Okay. So. Okay. Okay. So now, for the first hour or so, we're going to do the last classical part of the discussion of light, and I do promise that it will be no more than an hour. And then we will start to look at the quantization of the field. The beginning will be classical because, you know, well, okay, we'll discuss the quantization when we'll be there. That's a good question. I don't know. They all seem muted all the time, so you know, I can. David and Nave, are you there?
Yeah.
Okay. Okay, you got off the hook. Nice. Where's the? I don't know. That will turn on something. Or there. It's better to see them over there, but oh, maybe like this. Yeah. Success. Okay. And if you turn on your cameras, we'll actually see. Okay. So what's the plan? First of all, the plan is to use something that paints better. Then, first, I want to discuss let's call it like this. Classical photon statistics. Statistics. Now, how can you talk about classical photon statistics? That's the problem, because here we should put photon in brackets. Well, main thing is that people say photon statistics, but they don't mean anything that relates to photons. They actually mean electron statistics. Meaning you look at the statistics of what comes out of a photodetector. Now, if you believe that wrongly believe that every click of a photodetector is a photon, then maybe you're doing photon statistics. But the question of whether a click on a detector is actually a photon is, as we discussed, relates to many things. For example, it relates to the question of how efficient is the detector. What's the quantum efficiency of the detector? And that does require you to know of a single photon. So do you generate a single electron per single photon? And if you don't, which is what happens with most detectors are definitely not 100% efficient. And many of them are not even 10% efficient, or maybe even much less. Then the fact that you have a click doesn't tell you, well, it tells you something about the light, but it doesn't necessarily tell you anything about having a photon. And what we've mentioned several times is that there is, so instead of photon statistics, we should say electron statistics. And another thing that we should say is to take the time and go get better. There are no more, because those are going to die. So, so we're not going to talk about photon statistics and discuss about electron statistics or detection statistics. And this has to do with the fact that every detector by definition is noisy, just due to the fact that it detects that the detection events are discrete. Eventually, the detection events are discrete, not because of the light, but because of the matter. because of the fact that those are single electrons involved. So the point is that detection is a discrete process which inherently says that there's going to be noise. For example, we are going to show that if you have the perfect laser, which has a perfectly constant intensity, so the perfect light source, what it means, it has a perfectly constant intensity. Constant intensity. So suppose that you have perfectly constant intensity hitting a detector. So the situation that we're going to discuss is this. I have a detector that comes in. There's light that hits it. There's an intensity hitting this light. And that intensity may also be noisy. So, and then there's, and here we see,
She said it's perfect.
Wait, okay. I'm jumping. So we'll get to that in a moment. Forget this, okay? It will be explained. But if I have the perfect light source with exactly constant intensity, which means that I of t is just I0, constant thing, doesn't change in time, that will yield Poissonian electron statistic. Or, you know what, don't call it electron, detection statistics. So, and then, you know, people say, look, the photon statistics of a laser is Poissonian. Is it? I don't know. I mean, I don't know from it, or does this experiment where I take a really good laser, throw it on a photodetector, look at the output current, and now I have a problem because the intensity of light is usually I, and the current of light is also I. So,
What do you mean by person?
Small I. Okay, let's make that the current here. So what we want to discuss is the relation between. So now we go back to this, and I don't necessarily mean that this is so this is the model. We have light hitting a detector. This detector converts the light intensity into electrons. But now the point is that this detection, the probabilistic part is here. The detector is a probabilistic. That's where the noise could come in from. This, well, I don't know. It could be noisy, just as we discussed. We discussed coherence. You remember? So we know that sources could be random in the intensity that they generate, but this has nothing to do with quantization of the light. It's just the fact that they are classically noisy. So there's going to be here. This will be a classical source with intensity statistics. Here there's going to be a probabilistic detection. And we would like to take from knowing this and this, something about how this process of detection works, to say something about the statistics of, or the noise and the statistics of the generated photocurrent, because the photocurrent is what we measure. So that's the target. That is our target. Okay. Now, before we use the entire green all the day, because that's the only marker that works well, I'll try to get some better markers. Pauza.
אני גם רוצה פאוזה, אפשר? אני גם צריך פאוזה.
כל מה שאתה אומר נקלט עכשיו, משודר ביוטיוב, אז הכל בסדר.
אני צריך פאוזה.
כן. אבל אני צריך טושים. הם שחור במיוחד אין, אבל גם כחול יעזור. את כל הסט, תביא. כאילו, הירוק הוא היחיד שטוב שם. יופ.
יש לך דקה?
כן, אני אזרוק עכשיו. אוקיי. Wow, look what we got. Okay. So this one's still good, but the other two are bad. So let's kill them. Okay. Now this is confusing. How do I open this? Well. Okay, that's זה מבחן לניסיונאים. תיאורטיקן פשוט יוותר ויגיד, יוסי, תפתח את זה.
ועיבוד של ה...
מה? No offense to all the theoreticians of you. I have, some of my best friends are theoreticians. Yeah. No, הם מנוילנים אחד. Help me. One, you help me with this one, you help me with that one, and you help me with this one, and I'll do this one. No? תודה רבה, אתה מהיר ממני. מה זה? לא, זה כבר עשוי. אוקיי. לא טעים. תודה. אוקיי. So, this is what we're talking about. And then let's do this. So, we want to do what we call classical photon statistics or classical electron statistics. So, what we're thinking of is the following. So, I can say, let's say that P of t dt, that's a probability or probability density. So so P is the probability, it's the detection probability density at time t, which means that this is the probability of releasing, I don't know, one electron in time dt, during the time dt. And we can say that, look, this is proportional to the intensity or to the total energy absorbed during this time. We know that the integral of the intensity over time is the total energy or the energy density, but I assume here that everything is normalized to the area of the detector, okay? The detector has an area, so I would say if I want to be exact, I would write here there is some probability factor times the area of the detector times this. Now the area of the detector times the intensity is the total power that is that hits the detector. So this is the instantaneous power. And integral times dt, so that's the total energy. Now, but I'm going to absorb the area into this coefficient, okay? So because the area of every detector is fixed, I mean, areas do not change in time with most detectors. So we're going to assume, so I'm going to forget about the area and take just, okay. I'll say, look, all you have is the intensity here. So, or you know what, let's keep it here and then say that we call this thing together, we'll give it a different name. So, oh, I mean, we need this, there needs to be a coefficient here. We cannot make it 1 because those are not the same units. This is the probability of a photoelectron. This is, so there must be some coefficient with units that relates them. Yeah, and you can say that we measure the intensity in the units of probability. Okay, so but P of t dt equals this psi I of t dt. So this is the basic thing. So the assumption is that the probability for a short time, and now this needs to be really a short time. So dt is an infinitesimally short time over which the probability of generating 2 photoelectrons is negligible. So the probability of releasing just 1 photoelectron during that time is proportional to the intensity during that time. But, of course, now we're going to discuss times that are much longer than this. What happens over times that are considerably longer than this short infinitesimal time that we took, and then there definitely could be more than 1 detection event. And there definitely, and now we will ask ourselves, for example, what's the probability that over time t, large t, we will get n total detection events? And what will be the average n over large time t? And what will be its statistics? How much noise will it have? So the question is, so now taking, so this is the basic assumption. I don't know. If we were mathematicians, that would be the axioma.
Last lecture you said the intensity is not saying that the light is quantized.
Agreed.
So why now it's important in order to know how much photons we
we didn't say the word photon. I'm talking about photoelectrons. So those are, what's the, look, I mean, do you see here the word photon? No, it's not there. And so this is, it really, what we're discussing is classical detection statistics that has to do with the fact that the electrons are discrete. And therefore, if I look at a short enough time, if I ask myself, will I see an electron or will I not? And the answer is, you don't know. It's probabilistic. And the probability depends on the intensity of the light. So you know for sure that if the intensity of the light is 0 and you have an ideal detector that has no dark current, then the answer will be 0. So the question that we want to ask, just Q. The main question that we want to ask is, what is the average? Okay. So what is the, you know what, not average. What's the statistics of the detection events over a finite time t. Big T. So I'm going to ask myself, what is, so the question comes to what is, let's call this big P, M of T and T. What does it mean? This is the probability, real probability, to have M photodetection events over time window T, which starts at T. So I have a time window which starts at T and ends at T plus small t plus big T. Over this time window, I have an intensity, I don't know, that does something. This is I of t over this time window. And I ask myself, what's the probability that during this time t, we will have M photodetections? So that's the probability of M, exactly M, photo electrons over time window t to t plus big T. Now, of course, for example, if PM of small t and 0, if the duration of the window is 0, what is this probability? Yeah, the probability of detecting a photon during 0, not a photon, a photoelectron, during 0 time is 0. So now, okay. So I want to somehow say something about it. I don't know what it is, but I want to generate some form to express those. I want to build those probabilities. Okay? Now let's say what we expect. Okay? Something about this. Suppose that I took I'm using this lamp. That's my light source. I put a detector in front of it. It's a reasonable detector, not a really bad one. I mean, I know how to build really bad detectors, but this time I didn't. So I took a detector, I put it here, I left it an hour. What's the probability of seeing 0 photons? Well, I don't know if it's 0, but it's going to be really small. Yeah, okay. So the probability that the process is probabilistic. So basically there could be 0 photons or infinite number of electrons. This is not a probable assumption. Okay, during this, but if I leave it on for, I don't know, a nanosecond, maybe the result will be 0 because depends on the flux of photons here, electrons. But of course, it does depend. It's not an easy question. But what we do know is that there's going to be over this time, there's going to be some average number of detections. And you expect that the probability of having M will be peaked at the average photodetectors. It will have some width around it. I mean, there may be, so there is a probability. Suppose that the average M detection events is 1,000. What's the probability of 1001? Well, maybe there is. It can happen. What's the probability of 2000 events during the same time? What's the probability of 3000?
So it'll be some kind of Gaussian.
I don't know if it's going to, it could be Gaussian, it could be Poissonian, but this is what we're looking for. So there's going to be, probably, there's an average M, which is somehow related to the total, so what we expect. So, I don't know, the average M should somehow be related to this psi times the integral of I of t dt over t prime, dt prime from t prime equals, well, you know. This is the average number of photons, and we expect that this probability will be peaked. So we expect a peak here with some distribution. So now, so I want to show you how we can basically calculate this. We can say the following. So I'm going to start with the fact okay, so let's say this, Pm of t plus t prime plus, not, okay, so I don't know what this is. You know, it depends on many things. It depends on the intensity and how it behaves and its own statistics. I mean, if the intensity itself is noisy, maybe it affects the statistics of the detection. But what I can say is the probability of how is this related to this. So this is equals the probability of detecting m photons okay. So what I want to say is, look, I'm going to ask what's the probability of seeing m photons when I make the time window a little bit longer. Now, there are two options. One is that all photons arrived during the original window, and during dt, nothing happened. There was no detection. So that means that that's the probability that all of them arrived during this. All of the detections were in the original window. And what's the probability of no detection during this dt? This is this times 1 minus P of, yeah, well, where to go? Yeah. Yeah, t plus t, because that's where the, assuming that I do it, dt. What? No.
T plus t, dt.
No. This is the small p. This is the probability density. This is this one. I assume, okay, what we're saying is, look, I'm taking the time window, which is finite, and extending it by an infinite amount. During this infinitesimal time added, I neglect the possibility of more than one event. Most likely is that nothing will happen, and there may be a probability that one detection event will occur. But this time interval is so short that the probability of more than one detection is sufficiently small that we neglect it. Okay. Or there's another possibility, of course. The other possibility is that only m-1 detection events were during this time, and one detection event happened in the final dt that we assumed. So of course, Pm minus 1 of t. And the last one was detected so this means all detections occurred during the original window, and that's no detection in dt. And this is saying, now basically I should write here plus Pm minus 2 times something, but we assume, and two detection events during this time, but we assume that this dt is sufficiently short, that this is negligible, or this is just as we do always with infinitesimal or with derivatives, where all those higher orders, they are, we throw them out. So this is the same. Okay, so m minus 1. So I don't write everything. M minus 1 during t, and this is 1 detection during dt. Okay. So, and now this is a recursive. How do you say recursivi? זה אומרים בעברית.
Recursive.
In English also, I think they say something different. But this is a recurring. Well, recursive. I think recursivi. I think I've listened to Americans speak many times. They never say recursivi. יש לך? אוקיי. אז תבדוק את זה. תבדוק לי את העניין הזה ותחזור אליי, זה חשוב. Okay. So now, and this gives you a relation between Pm and Pm minus 1. Now, or we can, and now of course I can make it a derivative, because what will I do? I'll take, so I look at dPm to dt, which is nothing but Pm of t plus dt minus Pm of t and t divided by dt. So that means that I take this one to the other side and divide by dt, and that equals, so we now know this equals Pm, minus, of course, minus Pm of t times what? Yes. And what? No, nothing. What? Lo siyamti. I'm not finished. Wait. But so this times, and now I replace this p. So that would be psi times I of t plus t dt. That's the probability of detection. And that would be plus Pm minus 1 of t and t times the same thing. So actually, I could even write it simpler. Yeah, we'll do that. So let's, so I'm doing what, on the tablet it would have been simpler. So Pm minus 1 minus Pm, all of this multiplied by this psi times I of t plus t dt. Everything. Oh, no dt. dt was already divided. So now we have a set of coupled differential equations for the different probabilities and
Yeah.
yes, okay, can. Can. Those are, yeah. I mean, we're past that point, right? Okay, and then the point is, so this is what we have. We can write, so therefore we have dpm to dt equals, as we wrote, pm minus pm, sorry, pm minus 1 minus pm times psi I. And of course we can write dpm minus 1 to dt and all the way down to dp0 to dt. This is the probability of having no events during this time. And the point is that dp0 is convenient because p of minus 1 events is definitely 0. So here this cuts, and this is by definition equals only to minus p0 of, so I'll write it t times psi I of t. Okay. Now, by the way, this selection to, I can decide where I add the window to. So right now, why is it written here t plus t? Because I assume that I am adding the additional time at the end. I could at the same time said, no, I'm adding the additional time at the beginning. So the fact that it writes right here t plus t, small t plus t, I could write here just the same, just small t, which means, so if I do this, I can, so just for simplicity, we're going to do that. And that is to kill that one, which basically to think as if I'm adding the addition of the small time step at the beginning and not at the end. So this is saying that the window is actually like this. Here there is the dt, and from here is the big T. And this is where t is, and this is where t plus dt is. Okay, so I'll do it. Yeah, of course. So this is what okay. Now the last equation can be immediately solved. The last equation is not coupled to anything and we can immediately solve it. Is there a question? Well, yeah, because I can decide where my added dt is. So you know, what I was thinking originally was to say, look, I have a window that is t long, and then I added a small length at the end. And now I could say, no, well, I can add this wherever I want. Let's do it in the beginning. Okay? I'm looking at the time t, which is longer by dt, but where I put this dt is my choice. I can put it anywhere, in the beginning, in the end, wherever you want. in the middle if you want. I mean, I could write here even t plus half. Okay. So, I mean, this equation can be immediately solved. And this tells us that P0 of, so that's the probability of having no detection during those two times. That is e to the minus psi is out integral of I of t prime dt prime. So, yeah, I may vary as a function of time. And this is, of course, going from t to t plus t. And that makes sense. So the probability of no detection is proportional to is related to the total energy that hits the detector during that time. And the question is, and it's an exponentially decaying function of that. So that equals e to the minus total energy detected. Or hitting, well, not detected in this case. We should be careful. Hitting the detector. Now, basically from here, you can start building up. Because now, so you have, there's an immediate solution for the probability of no detection. And now we can write, so I can start building up and say that dp1 to dt, that equals, well, what we just wrote. P0 of t minus P1 times psi I. Okay. And so this one I know, then I can start building it up. But of course, I'll need to, very quickly we run into trouble because this one is exponential, and if now we'll need to assume something. I mean, we cannot solve conceptually. If I know I of t, I can solve all of them, at least numerically. But in reality, it's going to be a little bit complicated. So now we're going to do two. So now let's, but I assume now that, so this is in principle, if that's in principle possible, if I of t is known. I don't know if I of t is known. So this step can be done if we know the intensity. But if we don't, so now, what if I of t is not known? But we can say something about its statistics. For example, it has a correlation time. Maybe its correlation time is long. Maybe its correlation time is short. So those are the things that we can say something about. Okay. So now let's make, but this is hard. This is something that we don't know how to do. But let's look at what so I can say here. There is something that I can say. Wait. But there is still something that I can do. I told you that in principle this is, but you should look and see now. I can formally solve this equation. I can make a formal solution, assuming that I know something that I don't. What do I mean? Let's define, I can still do something that is called a formal solution. I'll define, let's call this I tilde of t and t. What is it? That's 1 over t. That's the average intensity over the window. Of course, from t to t plus big T. Now, this is a definition. I'll define this. So what did we find? We found that P, and let's have absorbed psi in it, just for convenience. So psi is inside. We absorbed it in it. So P0, and I'm not going to write all of this. So that will be short. E to the minus this I tilde. And now you can just check that under this assumption, we can see that the Pm is this. And with this definition, we can see that Pm equals what? So this is the average intensity over window. I must tell you, it's hot in here. And then we can write that this, and this is the important thing, this is this I tilde times t, sorry, this is of course time t. To the power of m divided by m factorial times e to the minus I tilde t. Or, and now look, this I can call, so this, what is this? This is, what do we have here? This is the total, this is the average number. What's written here, this I tilde times t, this is the average number of detections. That's what we expect. Look at this. By definition, this is just the, this is the total energy during the window divided by the time, but then we multiply by the time. So that, in any case, that's what we have here. And we expect that the average number of detections will be proportional to the average energy that is detected. So we can say that, look, this is the average number of photons, the number of detections, to the power of m divided by m e to the minus average m. Now this is a probability distribution that you know. This is Poissonian distribution under a specific assumption that the average m is constant. Or
how does the m plus 1 probability look like? So it should be lower than m.
Wait, okay. So then we can, so let's, we'll delay this for a moment. It's a good question, but so now we can say, you know, okay. Of course, this formula is correct only for m's that are non-zero. For m equals 0, we already know what the probability is. But you can check, you know, that this as a function of t does provide you with exactly the relation that we need. The relation. So what I'm saying is that this is a formal solution to our, and in a moment it will be crystal clear. So, but this is Poissonian. And this is something that we should, you know, this Pm equals average m to the power of m divided by m factorial e to the minus average m. This is something to keep like that. We should remember, however, that the average m is time dependent. That we now.
And we also need to remember that m of the probability is different than the m average. You don't necessarily look at the same number of detections.
Oh no, average m is just a number.
Yeah, so it's not.
And this one,
the same m.
No.
So.
No, oh, wait. To say that the average m, this is the same m, but this is the average of it. So tell me,
if you look at
okay,
zero,
look, I'm asking what's the probability of m detection during time t?
Basically, I mean, m that's not in the average, you can replace it with n based on what you wrote. Not
Which is n?
A different index, it doesn't have to
True.
be the same one.
No, it is the same index. It must be the same index.
This formula, let's say, we didn't see all like,
Wait.
general formula, that's exactly my problem. It seems like you wrote it just for a specific m.
No, I didn't. This is true for any m. Wait.
The question is the m.
Wait with the question because you'll understand. The average m is just what? Tell me what is the average intensity over the detection window?
Just some number.
That's it. So average m is a number which relates to the expected average number of detections. If you have a total energy, you know, if this energy generates a single event, so m times this energy on average will generate m events.
Yeah, but
so this
index, does the index necessarily have to be the same index as the average for the formula?
Yes, because this Pm tells me what is the probability of having m detection during a window, a big window t.
So what's the formula for a general index?
This is the general formula.
No,
that's for any. I'm telling you.
It has to be the average. I'm looking. I want to know what's the
True.
probability to get 2 photons.
No problem. P0, which is the probability to detect no photon, that's e to the minus m.
Yeah, okay.
And P1 is what? The average m to the power of 1 divided by 1 factorial, which is 1, times e to the minus average m. And if you want...
So the index doesn't have to be equal to the average. Like, it's basically confusing what you wrote.
I don't think it's confusing. I think it is correct.
Yeah, it's correct.
But at least, okay.
Same
So
index
confusing
was
is in the eyes of the beholder.
Same index was two different things.
No, I disagree. It's the same index for the same thing. This index goes for the actual number of detections that you actually saw. And this average is for the average number of detections that you could see in 1,000 measurements. You know, make many, many measurements, you'll get an average number of detections. Put it here. This would be the average number of detections. And then ask yourself, what's the probability that you actually saw How many cases did you see no detections at all? How many cases did you see 1 detection, 2 detection, 1,000,000 detection? And write those. And those turn out to be, okay.
Squared.
This one squared, yes. Now, and so on. Now, if you think about this, so, okay, so given a time as a function of, I'm writing as a function of big T. Okay, we'll be careful about this one in a moment. So now let's look at this. What is the problem with this solution? It's a perfectly beautiful solution, but we don't know this average M. So now we'll need to make some assumptions about it. First, and of course there are going to be 2 assumptions. One is that this average M is a constant, meaning that the intensity is a constant. The other case that we can check is if the intensity is fluctuating like crazy, too fast. So I remind you, so this is a nice solution. The question is, as we said, okay, so I'm sorry, but I'm not perfectly organized, but I'll try to be. So now let's assume, okay, problem. This average M, which now let's go back to defining it. This is psi times I average. Now this I average, it depends on both indices times T, this. This is unknown. So I have a formal solution, but I don't know. The result is going to be depending on both times and on the intensity, or knowing the average intensity, which I don't.
Does the average intensity have psi in it?
What?
Yeah,
you're right. We included the average intensity with psi. So you know what? Let's be consistent. Yeah. Okay. So how do we? So now first, but let's look at simple cases. I of t equals I average of t and t, the perfect laser. It's better to have this I average. You know what, let's keep, I'm sorry, I absorbed the psi and now I'm regretting it. So I'll put it back in, I'll remove it from here. I'll put back those psi's everywhere. And now they're no longer here, up to here, and then that's it. Because it's convenient that I and I average have the same units, okay? So that means in this simple case, this M average is just psi I0 t, and that's constant. And then the probability is indeed Poissonian. It's perfectly Poissonian. So you have a perfectly Poissonian process. So to say that a perfect laser has Poissonian statistics is wrong. The detection of a perfect laser has Poissonian statistics. And we can say, for example, now that if I ask myself, okay, so what are the different probabilities? So here is, so now the probability depends only on the duration of the window, on the time, on the duration of the window. And that's P0. And of course, this is P1, probability of a single photon, and there would be the probability P2, and so on. So tell me, yeah. Good.
So we can build some region constant in time.
What?
I mean, if we connect all the peaks.
Oh, nobody said that they're exactly the same.
Ah,
Have the same peak. You need to calculate them from the expression that we had before. But you can see that as we wrote, P0 is exponentially decaying. P1 is linear and then exponentially decaying. P2 is quadratic and then exponentially decaying. Okay. And you can... But now, and then the other extreme case that we can have is that the intensity is fluctuating a lot, but on a very short time scale. So that is the simple case. That was the simple case of constant intensity. So this is the simple cases. So this was constant intensity That's for the case of the perfect laser. And then, of course, the problem becomes hard to solve when we talk about, now the question is, okay. Let's see. I said simple case when perfectly constant intensity. Now, let me make this a little bit simpler. Okay. The intensity doesn't have to be really constant. I mean, it can change. It just should be constant over the window of detection. So if the time window that we take is shorter than the coherence time, the correlation time of the intensity. So suppose that I have a laser. It's not perfect, but its intensity is varying on a slow time scale. And my measurement time is shorter than the correlation time of the intensity. So that means that, which means that measure on time that is short relative to the I don't know. Well, what we wrote is to the correlation time, to the intensity correlation time. Or in other words, suppose now that you know the intensity is varying over a time scale. So the time of, so if I make a measurement over a time which is of this order, I don't know, something of, so let's say that this is something like tau c. Over such a time, you'll see a change. And if you're much longer than this, you'll see a change. But if your time t is much shorter, suppose that this is t, then it's fine. Then you could say that then in this case, I could say that this average m, which is a function of, will be a function of t only. It won't be a function of the big T. Why? Because then it's okay to assume that this is psi I of t. I assume that the intensity over this window, that's the only part that I need to care about, over this window is constant. So the intensity is changing, but the time window is sufficiently small so I can neglect the changes over this window. And then I can write so, and under this assumption, this remains. So all that changes is that the average becomes a time-dependent thing, and then still, so I can write this Pm of t and t. So assuming that this time, for short times, for sufficiently short times, the probability distribution will always be Poissonian. Okay? For sufficiently short times, over which the intensity doesn't change much, the probability is always Poissonian. Sorry, I shouldn't write this. So no average even. So it's just this. So this is for sufficiently short time. For sufficiently short windows, it's always Poissonian. Always. Woof. Now, what about longer time? Well, I don't know. Yeah. Then that's when we don't know. Okay. You're right. So I can, so for times that are very short compared to tau c, I don't know. For times that are for times that are very short, I know this was the solution. For times that are comparable, I don't know. But let's think about times that are much longer than the coherence time. Then, so for longer time, for t much larger than the coherence time, then it becomes easy because we need to assume a stationary source. So now we're going to say, look, I'm going to look over a time that is much longer than this. So the intensity is, and if we assume that, I don't know what the intensity is doing because it's a noisy process, but I can assume that it visits all the possibilities. Okay? Now then I would say something like, look, I'll need to or you know what, let's first say this. Under this assumption, and assuming a stationary intensity, I'm going to say that this Pm of t and t becomes just, it depends only on big T. But it doesn't depend on the time anymore. Because you are going over So you basically assume that you're averaging over all possibilities of intensities in there. This is like, this is an ergodic assumption, and now I'll have to say something about this. So, and that is to say, and what is this? This is actually this PM of T equals what? Some kind of, I can say that this is just let's say that this is the average of PM T over what? Over all possible starting times. And we can say average over ensemble of possible intensities. Okay, now we want to stop. Actually, so I'll just tell you where we're heading. I want to show you that for thermal light you get what? Planck statistics. But now we should, okay, so. And now, so now the question, so now it's this. So I want to explain what I want. I need to know the probability of a specific intensity. So this is like, so and this is loosely. So what's the probability of measuring a specific intensity? So let's think about the thermal light. For thermal light, that's simple, because for thermal light, I can say that the probability of a specific intensity goes like e to the minus that intensity. Well, you know, Boltzmann distribution tells you that the probability to see some energy is e to the minus that energy divided by kT. Okay? So that has to do with, like the probability of E equals e to the minus E divided by kT, where E is the energy, a specific energy state. Now, so, and that is, so this I is related, so I don't know, there's a coefficient here, but but if this is the probability of having intensities, we can calculate, and now you'll need to believe me because I'm going to skip some of the things, and then you'll get, under this assumption, you can calculate this PM of T average, which is this guy. And this turns out to be M average to the power of M divided by 1 plus I don't know if you remember, but this is Planck's law. Or at least this is the geometric distribution of possible energies and this is geometric. This is Planck. So let's stop here because I think that the main thing is clear. what did we see? So we saw that there's going to be a distribution always. There's always this probability. This is a probabilistic process, and there's always a distribution related to it. And the fact that you see Planck's law has to do with quantum mechanics, but it doesn't tell you anything about the quantum nature of the light. So do the clicks. They don't tell you anything about the quantum nature of the light. Both of them tell you something about the quantum nature of matter. And with this, I want to say one thing, that is that, okay, so there is one thing that cannot happen. That is to have sub-Poissonian statistics. Meaning, what does Poissonian mean? Poissonian means that the probability of detection is independent. At different times is uncorrelated. Okay? Meaning the intensity is constant, so the probability for detection at any time is constant. And it doesn't have any memory of what happened before or later. On the other hand, what we have is that the probability is proportional to the intensity of the light. So if now I have a detection event, it's most likely that now there is light. Okay, so if I see no detection event, maybe there is light and I didn't see one, or maybe but if I see a detection event, then there probably is light now. So what's the probability of having 2 detections or 3 detections over a short window? If I already have one detection, it's likely to have another. Okay? So, and that is, so either the worst case you could have is I don't know. If the intensity is constant, this probability is always constant. So the fact that you now have a detection event doesn't tell you anything about the future, because the probability, it's a probabilistic process with no memory. But if there is some intensity, fluctuating intensity, then the fact that you have a detection now tells you that it's likely that you'll have another. Now, to have the situation that if I had a detection now, there will be none later, this is something that cannot happen classically. But if you have a single photon source, it can.
Because classically you assume continuity in the function, in the intensity.
Yes, and you assume the intensity is only a probability. A single photon you cannot relate an average intensity to. Well, you can discuss about the total energy, but supposing now that I have, so now what we are interested in is this. I have here an intensity coming in, and I split it into 2 detectors, and I put here a detector and here a detector. Now, classically, those 2 detectors, they watch the same intensity. And I ask myself, but will they generate exactly the same currents? No, they won't, because they are different probabilistic processes. At some point, this one may click and the other one may not. Definitely at short times. Now, but suppose that this one did click. What's the probability that the other one clicks at the same time, during the same time window? Well, it depends, of course, on the average intensity, but it is more likely. I mean, it can be, if the intensity is constant, then there is no correlation between them, and you'll see a Poissonian probability. But if this intensity is fluctuating, then this saw a detection. It's likely that there is intensity. So there's intensity here as well. So it's likely that this one will also click. So the fact that I saw a detection here actually tells me that it's probably more likely to see an event at this one at the same time. But this is assuming a classical behavior. And if this is a single photon, then this single photon is going either here or there. And if I saw a detection here, I'll never see one there. This behavior, that would be non-classical. The fact, if I ask myself, what is, this is now tau, the delay between them. At the same time, So now I can, if this is a Poissonian case, then what's the probability of this one detecting at time? So this one is, I'm looking at, you know, P of t, and this one I'm looking at P of t plus tau. So what's the probability of both of them detecting about the same time? Of course, there's a window around, assuming an averaging window of the detectors. So if this is a constant, that's the best case. That's a laser, a perfect laser. And for classical light, it would look like this. We plotted it before. And this duration is the coherence time of the light. So if you're looking at, if those two detectors are looking within, so the probability of detecting on both of them, that's the probability, that's the coincidence probability. Coincidence, oh God. Probability. Maybe we should go back to tablets because there things become more clear. But to see something like this, that is impossible classically. But it is possible for a single photon source. So there are two ways to quantize a field. There are two ways to quantize a system. One is to write its Hamiltonian, identify its conjugate variables. What is the canonic position and canonic momentum? So I can do, so how do we quantize? Quantization. So, well, the subject is, of course, quantization of the electromagnetic field. And we want to see how photons come about. So how do we quantize something, a system at all? So the answer is always, so the general way is write a Lagrangian. Generate from it a Hamiltonian. Which, you know, a Lagrangian which relates to the kinetic energy, and you generate from it a Hamiltonian. And in this Hamiltonian there will be this canonic momenta and positions. This Lagrangian is a function of those positions and their derivative. And then this P is the derivative of the Lagrangian according to Q dot. Those are the general momenta. And then what we say is, look, those are not, once we do this, we have the Hamiltonian. Quantization says, take, where this is, say that replace the P by the operator P, replace Q by the operator Q, and declare canonic commutation relations between them. So this is that's the way, that's the very standard way of quantizing something. And basically we can do that for the electromagnetic field. I mean, we can write the electromagnetic Hamiltonian, and we can start quantization from there. But there's another way which is simpler, and that is I can write, eventually we will write the Hamiltonian, but there is a convenient way. Nobody said, there is a great freedom in selecting those conjugate those variables, those, those. A position in analytical mechanics is a generalized position. It could be an angle, it could be whatever generalized coordinate you can think of. All of those are possible. Now basically what we were going to use is to look, first we're going to do the classical modal decomposition of the electric field. So what we are going to do is first classical modal decomposition of the electromagnetic field. And then we're going to identify each mode as a harmonic oscillator. We'll see that the Hamiltonian of every, if you choose your modes, right? The Hamiltonian of every mode is just the Hamiltonian of a harmonic oscillator. And then we don't need, we already solved the harmonic oscillator a sufficient number of times, so we can immediately quantize. Rely on this to quantize, and then rely on what we know from the harmonic oscillator. So that's basically what we're going to do. So let's very quickly do the classical part of what we're doing. Well, we start from Maxwell's equations. Curl E equals minus. So I'm doing this in and 1 over mu naught curl B equals epsilon. Of course, all of those are vectors, but I'll write the vectors just for to remember. So this is equation 1, and this would be equation 2, and then there are those 3 equations that has to do with the divergence of E equals equals rho, and divergence of B equals 0. Okay, but we know that we can write both of them as derived from vector potential and scalar potential. We know that we can always write, so we can define A, vector potential A, and the scalar potential phi, and we know that we can always write B as being the curl of A, which immediately gives you this. And we can write E as being the gradient of phi. But this is assuming this is the case of a stationary field, but when there is time dependence because of this part, we will get minus or plus, it's minus dA to dt, minus לפני הגרדיאנט, בסדר. And then, and if we write, I'll take this, put it in here, and take this, put it in there. I can write the wave equations for the potentials. Okay, so I'm taking equation 2. And that will lead, and I'm sure that you've all seen this, to this expression. Okay, so all that I need to tell you is that del squared A, this is a vector relation, plus 1 over c squared plus 1 over c squared equals u0j. And now, and of course for the potential, I can take this and put it in here and get, this is taking equations 2 and 3. They lead to this. Where I'm losing something, maybe, here I forgot. Epsilon naught del squared phi. What? There is no scalar. Yeah, you're right. There should be, of course, gradient of phi. I'm sorry. Yeah, it's a good question.
It should be only one
Good point. You're right. Oh, well, in a moment we'll throw this one away. We'll choose a gauge. We'll choose the Coulomb gauge where this goes away. Here we have minus epsilon naught gradient, divergence of dA to dt. That equals rho. Okay. Now, so those are two equations. I'd rather have them more nice, meaning I want the first one to be just a wave equation. I don't like this term. You saw I made too many mistakes about it. I forgot the grade. I don't like it. I want to throw it away. And the same goes for this one. I want the lower equations to be just the standard Poisson equation. Poisson or Laplace? That's Poisson. Poisson equation that we know and love. So what do? I can always choose gauge. I can decide. We already know always that A, we can do a gauge transformation where A goes to, or let's say A prime equals A plus some gradient of any function psi that is a function, can be a function of both R and T. When you do this, the field, of course for the magnetic field there's no change because the curl of a gradient is always 0. So curl of A equals curl of A prime. So, and that equals, that doesn't change the field at all. And what about the electric field? The electric field could change because the electric field includes the A to dt. But that means that at the same time, I need to gauge also my potential. So we'll have phi equals phi prime equals the original phi minus. Let's see, does this work? I think so. Now, but the point is that I can choose any such any function where chi is the gauge function. And this is completely arbitrary. I can choose any chi I want. If I assume those that the vector potential transforms according to this, and the scalar potential if it's a scalar potential, so how do you write vector? Then this leaves E and B the same. They don't change. So we can do this, and specifically we can choose chi such that the divergence of A is 0. So I can choose chi such, so I want the which basically means that Laplacian of chi equals the divergence of the original A. Now this is something that can always be solved. The divergence of A is some function, and this is just the Poisson equation. The Poisson equation can always be solved. So what is this chi that does this? It solves the Poisson equation related to the divergence that you had before. And under this assumption, what will happen is that this guy will die out, because the divergence, we can always exchange orders. That's already, you already feel convenient with it, and you're not. Yeah, you're already good. We are all physicists, so we know that this means immediately that we can throw this one out due to the gauge. By choosing this gauge, which is called the Coulomb gauge. So this is called the Coulomb gauge. Well, you know, Coulomb, that was his name. He was Coulomb. But every American will tell you that this is the Coulomb gauge. Okay, and then let's remind ourselves why this guy will fall down, because the gradient of phi will be, yeah, you see, well, we'll have the gradient of the chi to dt, which is like d to dt, the gradient of chi, and then this guy falls also. We said that phi is also exchanged under this assumption. So, and when we do this assumption, what will be the solution? So this is what it is, and of course what it means is also that believe me, okay, check it yourself. Those two, they fall under the gauge. So then that means that our equations become convenient. Yeah. Maybe there should have been a minus here. I'm sorry. So 1 over c squared, this minus equals U0 J. So this we didn't, and then so, and all we did so far was just take a gauge. And del L squared of phi equals rho divided by epsilon. So now, so under the Coulomb gauge, those two are conveniently separated. What? I don't think so.
You needed to add the D inside the T, and there will be a gradient of it. Oh.
What? No.
No, because you put the psi tag, phi tag there, no?
No, this is fine. I'm assuming.
If you put in phi tag, you get another part.
No, I think that is fine, and I'm quite certain that it is fine, and I don't want to waste time on making sure, because I'm certain that it's fine, but I don't remember how. So yeah. Okay, and then so now. Where did we go? Yep. 4. And there is another important thing. So those are the two. So this one is the second equation looks like the standard electrostatic equation that we always know, even though the density, the charge density can be time dependent, and of course the currents can be time dependent. We should remember though that there's a relation between the current and the charge density. They are related by this. So those are, so we can say that, you know, so those are the three equations that relate all the relevant quantities. And now I can write, so let me write, I'm going to write J as two components, longitudinal, something that we call longitudinal J, and transverse. Those are just Y, so I'm separating it like this, Y, because, well, J is a vector field. That's a vector field. Now, I can always take it, define it according to the part that has no divergence. It does, so, and I'm going, they are defined in the following way. The longitudinal part, sorry, the transverse part has no divergence. And the longitudinal part has no curl. Why can we always do this? Well, it has to do with the fact that you can always, for example, it's doing the following. I can look at J and say J plus gradient of some function f minus the gradient of the same function f. I don't know what this function f is. That's still J. Now I'm going to choose this function such that okay, I'm going to choose this function such that the divergence of j plus gradient of f is 0, which would be the transverse part. And then, and since this is a gradient of something, then the curl of this gradient of f, that's 0 by definition. So we'll call this the transverse j, and we'll call this the longitudinal part of j. Now you can always, and what do you need to do in order to find this? You need to find the function that makes this be 0. So you want to make sure that, again, this curl, this equals minus the divergence of j. So I need again to solve this Poisson equation for f, which can always be done. And then I'll know what is the function that I need in order to separate j into a longitudinal part and to a transverse part. What?
I didn't understand
What?
why you put F.
Oh no, this is just to justify my statement that I can always split the current into two independent currents. One of them has no curl and the other one has no divergence.
Okay. So you put it in order to...
Why is that important? Because in a moment I'm going to look at what happens if I take a curl of this equation. So and then we'll see that all that is important is just the transverse part of the current, and the longitudinal part I can throw away, for example. So I'm going to use this breaking of the current into longitudinal and transverse part to say that I care only about one of them. Yes.
I have to say that I can't see how to get from here to the Lagrangian and the Hamiltonian and quantize this.
We haven't done that yet. Well, it will take some time, but not a lot. That will happen. Okay. You know, this is an excellent question because to get there, it will take us 5 minutes. Yep. You were saying that I was missing something? Yeah. Let me remind myself. Ah, yes. And we were too quick to kill something, and I should be sorry. Yeah. It was here, plus 1 over c squared d2 dt, gradient of phi, and that equals mu 0 j. And then I told you, I didn't want to kill that one yet. Why? Because now, under this assumption of having a longitudinal and transverse components of the current, I can say the following. Well, you know that the curl of a gradient is 0. Now, because the curl of a gradient is 0, then we can write the following. This relates only to the transverse part of the current. And the other part, which has to do with this, 1 over c squared d2 dt gradient of phi, this one relates to the longitudinal part. And this is the result of what we just did. Now, okay. So all of this was long just to make things very general. Now I'm going to look. So now let's allow ourselves to look where there are no currents or charges. So we're going to look at So I'm saying that rho equals 0 and j equals 0. But of course, that doesn't mean that there is no field. There's definitely a field over there. Okay. So, and then what do I want to say? Yes, so now we can write, when under this assumption, then this becomes just a simple wave equation. Now, how to solve this? Modal decomposition. So now we need to define, so we can decompose this, and we know exactly how we're going to decompose this as plane waves. But you can take any set of modes that you would like. So then I could say, look, this is equal to what? A sum over all possible k vectors. And honestly, there's also polarization. So this is k vector, and this is polarization so there is time, this is the vector that tells you which direction of E is, of A is, times A k lambda, and this is these are scalar functions of R and T, where those AK of those functions are equal to just some some ak lambda e to the I k dot r minus omega t plus complex conjugate. Do we agree about that? And those k's, okay, so this is just a, what did we do? We have a plane wave solution. There is a relation, of course, between omega and k. Omega equals c times absolute value of k. And k, assuming now that we are within some volume, so this is in volume L cubed, k is a vector which is 2 pi, or just pi over L outside times 2 pi, and x and y and z when those are integers. Those are just the modes of, yeah?
What is this exponent
In the first term, in A vector? No, above.
Oh, there's no exponent, I'm sorry. This is just to say, this is the vector. This defines, you know, here I have a vector. This is a vector field. So it must have a direction as a function of space and time. Each of these modes is a scalar function multiplied by a constant direction. So this constant direction, for every mode, there is its, and indeed basically there are two polarizations for this, and then I'll leave that part and go up. That's okay. I mean, we can always express the solution as some of those modes, meaning we can always find those, what do we need? Basically, we need coefficients, a set of coefficients. And this set of coefficients we can also always find by just basically a Fourier transform. Correct. And then, by the way, we can talk about linear polarizations. We can actually even choose, choosing our basis is the way we like it. We can also use right and left circular polarizations. They are just as good a basis as the other one. What's the time? Okay. We have 15 minutes, which is perfect to finish the quantization. Okay. So basically what we are assuming, we're saying, look, we have a mode so that's what happens for the vector potential. Now we just said that under the assumption where there is no currents, then the electric field, the magnetic field is the curl of A. Now, and the electric field is, well, what is it? Is minus dA to dt. Right? I erased everything, but I think that's fine. Yep. But this one what is it? So this would be still, I'll take this. So it would be sum over k and lambda. And then what? There will be, I'm going to take the kernel of this function. And what we'll have is this vector ek and lambda cross with the vector k. There's going to be an I outside. You know what? No, I'll keep the I for later. And this will be multiplied by what? By this same function. A k lambda e to the I k dot r minus omega t plus, sorry, and here we should be careful. Where does this k come from? It comes from the derivative of this relative to r. So once it will come down with ik, and in the other case it would come down with minus ik. So I'll put here a minus complex conjugate, and there will be an I here. Now that's okay. This I doesn't mean that the things here are complex. This I is exactly what you need to make this thing real, right? Because when you take something minus the complex conjugate, you get something that's imaginary. And what about this guy? Well, that's simple as well. This will be I omega coming out. So it will be the same thing, sum over k and lambda. And here we'll have E times I omega times the same thing. Maybe there was a minus sign, but that doesn't matter. So now we know everything. We know the vector potential and we know the field. And now we can write the Hamiltonian. Because the Hamiltonian in this case is the total energy, or I can write the total energy, which is the total energy. That is what? That is the integral over, there is a factor. I think it's a half, but I don't remember. The main point is that there is an integral over the volume. It's called volume over the entire volume of what? Of E squared plus B squared.
All of a sudden the plane wave wasn't that good.
What?
All of a sudden the plane wave.
No, the plane waves are perfect. Why? Because, let's see, E squared will contain what? There will be terms like e to the I k dot r, and then there will be e to the I k dot r prime, because here we need to be, but then we'll have a delta function. So what will happen here? You'll take those, you'll put them in. There will be this sum. The sum comes in here twice. And this sum comes in here twice. There's sum over k and k prime. But you integrate over r, so you'll get a delta function. And I can what I want to remind you is that the integral of e to the I k dot r minus r prime oh, sorry, not this. K minus k prime dot r is a delta of k minus k prime. Yeah, d3r. True. So under this reminder, I'll tell you that what you get is this. So I can say that, the total energy equals what? Well, basically there will be this half, and I'll have sum over k and lambda and sum over k prime and lambda prime, and we'll write, and there will be the total volume in here, because we integrate over the volume, and we cannot assume that it is completely infinite. It's large, but it's not infinite. And here we will have a k lambda a star k prime lambda prime plus a star a of the same thing, and all this is multiplied by something that will be here, some vector direction. I don't care about it, because the main thing is that we will have here, and then there will be the and there, I'm sorry, yeah, there should be a delta. What is written here is incomplete for a moment, but I'll write what is correct. Half sum over k. What? Epsilon 0. Omega k squared volume times now. That's what you would get here. What?
What's the delta function? You should have delta.
That's already taken care of, because as we know, there should be two sums here, and the delta kills one of them. The delta of k minus k prime is what makes sure that this is a k lambda multiplied by its own complex conjugate. If this is something that you don't immediately see, we can slowly show, but yeah. Now I want to write this in the following way. So I want to make it, sorry, this half shouldn't be here. There's no half now, but I'll write this as being as half of what? A k lambda a star k lambda plus now classically this is nonsense. Well, it's not nonsense, it's correct. It just it's not clear why should I do that. But now I want to tell you, okay, so what do we have here? We have here sum over modes, where the total energy equals this, the total energy is equal to the energy of each mode, sum over all modes and calculate their energies. And each mode contributes something that looks like this. Why did I write it? Do you remember the Hamiltonian of the harmonic oscillator written in terms of the ladder or the creation or annihilation operators? The Hamiltonian, so I can say now that the classical Hamiltonian of each of mode k and lambda, let's not carry this with us, is this half outside epsilon naught v omega k squared times this. plus what is written here. Now, the classical Hamiltonian, sorry, the quantum Hamiltonian of an okay, and moreover, we know that each of these modes is a harmonic oscillator. It's time dependence. You know, that's what it does. It oscillates in a way that a harmonic oscillator does. So each of these modes is a harmonic oscillator, and I want to write, so they are classically, each one of them operates like a harmonic oscillator. And each one of them, and if we think about a quantum harmonic oscillator, it also has and you know that this goes like h bar omega times a dagger a plus half. Or we can write it also as being half h bar omega times a dagger a plus a dagger. Why? Because the commutator of a and a dagger is 1. And yeah, because the commutator of a and a dagger in 1. And this, so now we did something quantum, okay? So now we wrote, okay, wait, all of those, they are harmonic oscillators. I wrote the Hamiltonian of that harmonic oscillator, and this looks very much like the Hamiltonian of the harmonic oscillator, the quantum harmonic oscillator written in the language of creation and annihilation operators. Or, of course, I could write the Hamiltonian as being as a function of, you know, p squared plus q squared under the correct choice of, right, there's probably omega somewhere, but wait in a second. Which is, you know, and we know that this P and Q, they have a relation of IH bar, or let me write it, let's be more correct. I should write, normally we write P squared over 2M plus, let's write it like that. Plus half, yeah, to be correct. Where did I go? Plus half m omega squared q squared. This is the standard thing, but we know that we can write this as being, again, h bar omega times a dagger a plus 1 plus half. Where does this, and this has to do, this is the standard relation of those guys, and we define a as being, yeah. And we define a as being 1 over square root of 2m h bar omega times m omega q plus I p. And if we assume that, and under this definition of the creation operator, sorry, the annihilation operator, we know that, and assuming that this is the commutation between P and Q, then we get, this is the definition, that the commutation of A and A dagger is just 1. Okay. So what do we need to do now in order to quantize the field? We need to identify the creation and annihilation operators. What do they relate to classically? That's actually the point. This is what is convenient. These A and A dagger relate to the amplitudes of the different modes. So if I want to say, I can say that the classical amplitude of the mode k lambda is translated to the annihilation operator in mode k lambda. So that is the quantization step. And that, of course, at the same time, this star is translated into and instead of assuming that those two are classical numbers that are basically complex conjugates of one another, those are quantum operators that are Hermitian conjugates of one another, and that have a quantum. And once we said this and assume that they have this commutation relation, this is when we quantize the field. Now, what do they mean? Well, now we met the photon. Why? Because you know for the classical harmonic, for the mechanical harmonic oscillator, you know exactly what this creation and annihilation operator does. It takes you from state number of energy n to energy of n plus 1 or n minus 1. I assume you have all seen creation and annihilation operators before. Okay, yes. So if you didn't, say that you didn't. Or be silent forever. What? No, I think you've seen that also in quantum mechanics 1, or no?
Yes.
Yeah. Quantum 1, yeah. So the fact that so then now think about this. The creation and annihilation operator takes you from state with n and takes you up to state of energy n plus 1 or n minus 1. Now you always think of this, those are states of the quantum harmonic oscillator. There's the 0 state, the ground state, with 0 energy, or half h bar omega, but everything is relative, so let's call that 0. And there's the 1 state, which is exactly with 1 h bar omega quantum, and 2 and 3 and 4. Here it's the same. The same thing happens. Because the Hamiltonian of the mode k and lambda is still h bar omega k times a k lambda a dagger a. Well, you can do it like that, plus half. It's the same thing. And now, what does this create or annihilate? It creates quanta of energy of that mode. So, just like the harmonic oscillator has a quantized energy and has Hermite-Gauss states. So each mode of the electric field, or sorry, of the electromagnetic field, is a harmonic oscillator. And its energy is also quantized. It can have an energy of 0, which apparently is not 0 because there's this vacuum. The zero energy of a quantum harmonic oscillator is not perfectly 0, and it's definitely, it has some uncertainty of x and some uncertainty of p. How does that relate to what we do here? But those create and annihilate photons in the mode k lambda of the electromagnetic field. And a photon is a quantum of energy. Now the question is, where does the Hermite-Gauss wave function come to play? In which, what is what are, or in what, sorry, in what, no, space does this thing oscillate? Now let's try to remember. If I have a mass on a spring, well, yeah, well, okay. Just wrote it and then, what's the time? Oh, that's too late. So I'll just say something very quickly. If we have a mass on a spring, then you know, okay, I have this spring and then here is my mass. And this mass is oscillating back and forth, so this is my Q, and P is the momentum. And we have this wave function as a function of Q, which is the Hermite-Gauss wave. So the quantum wave function, which tells me what's the probability of finding Q somewhere. Now let's remind ourselves, what is Q in terms of this is A plus A dagger. There's a coefficient up front, but that doesn't, forget about that. It is proportional to A plus A dagger. And P is proportional to A minus A dagger times I. What are they? So this goes like A k lambda plus A star. What is this? That's just the real part of the amplitude, of the field amplitude. What is this? So that's the imaginary part of the so that would goes like A times. So this is just the real part of A and K lambda. And this is just the imaginary part of A, K, and lambda. So it's the field itself. We saw it. Those are field operators. So where are X and P? They're also in the field. The field itself is the oscillation. This is the amplitude of oscillation. Here, what oscillates? X. Here, what oscillates? The field. The field itself is oscillating. This is what goes up and down. So what becomes quantum is the field. And you'll have now, so this is, so Q is like this, the real part of that. And P is like the imaginary part of it. And what it tells you, for example, because you cannot know both Q and P because they are not commuting, then you cannot know both the real part of A and the imaginary part of A at the same time. You cannot measure both of them at the same time. Just in the same way. So I think here we'll stop. although I can go on forever because this is a subject that I really like. But we are already over time. So I'll answer questions. What we did was to quantize the field. How? We assumed, we said, okay, let's look classically until we write the field as a sum of harmonic oscillators. We saw something that looks exactly like a quantum harmonic oscillator for two reasons. One, those modes are harmonic oscillator solutions. And two, this thing looks exactly like A dagger A plus A dagger, or which is what you want to see in the standard quantum harmonic oscillator. And then we said, okay, we identify them like this. By the way, I could do the identification here. I could say, look, I identify Q as the real part and P and as the imaginary part. I assume commutation relations and get this. But it's the same thing. Okay. I'll stop here. I guess what you will do in the tutorial and also with me next time would be to start looking at, let's look at a single mode. Let's write everything. Things will be more accurate and proper, and all the relations will be related, and then we'll see, well, what this was looking at the vector potential. What about the field? Well, there's not much different between the field and the vector potential. The only difference is that there's this omega k here. So if I ask myself, what is the field operator? The field operator is basically the same, just multiplied by I omega. What about the operator of the magnetic field? Well, it's also about the same. It's the same thing, just multiplied by, so okay, so there's, let's forget this. There is a direction that comes from this cross product, but other than this, it's just ik times that. And k is omega divided by c. So they're also, so what is the, so this A, they are the operators of the vector potential, but also of the magnetic field and also of the electric field. So if I ask, what is the electric field operator? It's A times I omega. So, but this is just a normalization factor. There is a normalization here that we neglected, and we should add, and it will be there, and it includes the volume, of course, and all of and epsilon 0, but all of those will be there. But so what you see is that once we know this, yeah, this creation and annihilation operators are the operators of the vector potential and of the electric field and of the magnetic field, only multiplied by some simple constants. So, and now is a good time to stop and continue next week. Do we meet next week? Yeah. We meet next week. After that, there's Shavuot, but I don't think it collides with our meeting. I don't know. What? I think that Shavuot is Sunday and Monday, and we meet on Tuesday. אז ב-18 לא נפגשים? then we need, אנחנו נצטרך להשלים את זה, אני מצטער. Oh, we'll see. There will be something.